Section 5.3 today, Riemann sums and definite integrals. The objectives are going to be to understand the definition of a Riemann sum, to evaluate definite integrals using geometry and using properties of definite integrals. We'll review these objectives at the end. So the first definition is for a Riemann sum. Let f be defined on the closed interval and let x1, x2, x3, etc. be any numbers in that interval from least to greatest. Then the sum of the area of the rectangles that can be defined with these values is called a Riemann sum. We'll see that in the following example. So here we have a table of values with x and y, and we are asked to find the Riemann sum using LRAM. So if we sketch the points 0, 12, 10, 24, 30, 28, 45, 20, 60, 16 and draw the rectangles, this is what we get. And notice how the last point 60, 16 is irrelevant in that problem because we're using a left approximation. So here we have four rectangles. This is a Riemann sum. We have to add the area of these rectangles. First rectangle 10 times 12, second one 20 times 24, 15 times 28, 15 times 20. So we have four rectangles and the total area is 1320. As you can notice from the previous example, the rectangles don't necessarily have the same width. So, a few definitions that we've seen before. This time we have a lower limit of integration, upper limit of integration that's new, but most of them we've seen before. Remember to always check the variable of integration. So when we define an integral formally, we define it as the sum of rectangles as these rectangles grow in number, so they approach infinity, and each rectangle's area approaches 0. So this is how limits ties into integrals, because an integral is the limit as n approaches infinity, n being the number of rectangles. We won't do very much of that. I'll show you one example here. The interval 1, 3 is partitioned into n subintervals, and mk is the midpoint of the kth interval. So if we have these subintervals, and this is a function with mk being the midpoint, then if we add them up and n approaches infinity, we can simply write this sum as an infinite sum, and this is what it looks like. So straightforward, the interval 1, 3 is written here. We integrate from 1 to 3, and the midpoints mk now come up as x. Delta x, which was still measurable, now became dx. It's a differential. So more about areas now. If f is non-negative and integrable over the closed interval ab, then the area under the curve from a to b is the integral f from a to b. If f is negative, then the area is minus integral from a to b of f of x dx. This is why we call the integral a signed area. As long as we are above the x-axis, it represents the area, but once the graph goes below the x-axis, then we have to change the sign. So the area is always positive, but the integral can be negative. So we'll do a few studies, or two studies of integrals using geometry. This is, from here, it's really important to understand what's happening. So if we want to evaluate the integral from -2 to 2 of root 4 minus x squared dx, when we sketch the graph of f of x equals root 4 minus x squared, we see that it's a semicircle, and that's an easy area to calculate. We know that since the Greeks. So the area of a circle is pi r squared, the area of this semicircle is pi r squared over 2. Therefore, the integral from negative 2 to 2 is pi r squared divided by 2. The radius is 2, so the answer is 2 pi. Second example, if we graph absolute value of x over x, f of x equals absolute value of x over x, this is what it looks like. And here we have part of our integral that is going to be a negative area, a signed area, so we have to be careful. The area here is 1, because we are going from negative 1 to 0, and beyond the y-axis we're going from x equals 0 to x equals 4, so that area is 4. Here the area is 1, but be careful, the integral is negative 1, so if you write integral from negative 1 to 0 of absolute value of x over x dx, you have to write equal negative 1. So what's the integral from negative 1 to 4? It's negative 1 plus 4. So this negative 1 plus 4. Answer 3. We're going to study a few properties now, and we can use these properties to find values of integrals too. Many of them are quite intuitive, and I think it's worth thinking about the answers before you just copy them down. So if the integral from a to b of f of x is given, then the integral from b to a, if you integrate from right to left, which is unusual, what you get is actually minus integral from a to b of f of x dx. What happens if you integrate from a to a? Well, if you think of integrals as an area, what could that be? It's obviously 0. It's the integral, it's going to define an area that has no width, so the integral is 0. C, if you integrate k times f of x, this is a vertical stretch. You had a graph, you stretched it with a factor k vertically, then the integral is going to be k times the original integral. And that same property with k equals negative 1, so if you want to integrate negative f of x, here k is negative 1, then obviously that's equal to negative the integral of from a to b of f of x dx. Property D, if you add functions together, you can simply integrate each term separately. So the integral of f plus g would be the integral of f plus the integral of g, which we do all the time when we integrate polynomials, for example. The integral of 2x plus 5, we just integrate 2x, we integrate 5, and we put them together. Now this property E is interesting geometrically. You'll have to think about it for a second. If we integrate a given function f, the same one, from a to b, and then we add the integral from b to c, this is what it looks like. We integrate from a to b plus the integral from b to c. What is it going to be? It's going to be the integral from a to c. It's like integrating directly from a all the way to c. Property f tells us that the integral from a to b of f of x is bounded by two values. It's bounded by the area of that rectangle here. That's going to be less than or equal to the area of under the curve. And the area under the curve is also bounded by that big rectangle here. So this is quite obvious when you look at this graph. And how do we define these rectangles? This rectangle here is defined as base times height, and the height is the minimum value of f on the interval. It happens here that the minimum value of f is at x equals a. So if you do base times height, you get the area of this rectangle. Base times height is here, base times height. You can do exactly the same with the maximum value of the function on the interval. It happens somewhere here. We could call this point C. F of C is the highest. It's the maximum value of the function on the interval AB, and therefore the area under the curve is bound to be less than or equal to the area of that rectangle. Again, base times height is base is b minus a times height, which I just called f of c. Here it's called the max of f. Finally, if a function f is everywhere greater or equal to a function g, then naturally the area under the curve of f is going to be greater or equal to the area under the curve of g. So a few examples. This isn't very hard. If we know that the integral from -2 to 3 of f of x is 5, and then the integral from 3 to 5 of that same function is -1, then if we integrate from -2 to 5, it's basically -2 to 3 plus 3 to 5. We're going to have 5 plus -1 equals 4. Try to find which property this is. It's property E. Now the integral from 3 to -2 of f of x dx is equal to -5. And which property is that? It's property A. We will use property F now to show that the value of this function has to be less than 1.5. So if we look at the second part of property F, the integral from 0 to 1 of that function has to be less than or equal to the maximum of the function on the interval times b minus a, here 1 minus 0. So what we want to find out is what the maximum of root 1 plus cosine x is on that interval. Well, the maximum value is when x equals 0. At x equals 0, cosine of 0 equals 1, and therefore the maximum of the function is root 2. So if I plug this in here, the integral from 0 to 1 of the function is less than or equal to root 2. Root 2 is 1.41, so if it's less than or equal to 1.41, then it's bound to be strictly less than 1.45. The worst we could have is that it's equal to root 2, so it's necessarily less than 1.5. So let's go over the objectives again. We saw that the Riemann sum is the sum of the areas of rectangles that are defined by a function. We saw that we can find integrals using properties of geometry. And finally, we saw a few properties of definite integrals which allow us to find more integrals.